Okay.
Okay, welcome everyone to the monthly Software Computing Roundtable. This month is back to analysis, techniques and tools is the general topic. So as usual, there's 3 talks, about 30 minutes each, including time for discussion. And the first one is Matthew Shepard from Indiana University. His research program includes light meson spectroscopy with GluX, JLab, and S3 in Beijing, and he's currently the spokesperson of the GluX collaboration. And he's going to tell us about AmpTools. So go ahead, Matthew.
Yep, you can hear me okay?
Yes.
Good, all right. All right, so I apologize in advance. I'm actually on site at Jefferson Lab on shift collecting data now. So hopefully things will go smoothly, but there may be some background noise, but that's fine. So thanks for the opportunity to tell you about amplitude analysis with AmpTools. I'm probably anticipating a blend of computer science background people and physics background people. So hopefully I'll hit the target audience right. And to do that, I want to tell you a little bit about what we're trying to analyze in amplitude analysis. So a little bit of physics, what are we looking for? And what's the method, the general method? And then I'll talk about the method of maximum likelihood estimation. So if you're familiar with fitting models to data, this is a very common strategy, but it's worth reviewing because it makes up the core of amplitude analysis and the approach to amplitude analysis. And then I'll talk about the implementation with this software package called AmpTools. And this has more of the computer nuts and bolts in it that may be of interest to people. And stop me at any time. Just raise your hand if you have questions. I have the Zoom window open, and so I think I should be able to answer questions. So amplitudes. So what are the ideas here? Right. So the going back to quantum mechanics, you formulate what happens in nature in terms of complex valued functions. They're typically written in terms of kinematics, like the 4 vectors or momenta of the particle or something. And if you want to predict the probability that something happens, then you coherently sum all these indistinguishable paths, and you take like the absolute square of this to compute what's the intensity in quantum mechanics and figure out the probability of an event happening. And so there's some ideas there. One of the core ideas is that indistinguishable initial and final states interfere with each other, right? This is like the double slit experiment. You have a path through one slit and a path through the other slit, and they coherently interfere to produce the interference pattern that you see. So that's one key idea. And then also you have to sum over all the distinguishable final states. So if the final states, for example, have different orientations of spin, in principle, those are distinguishable if you had a Stern-Gerlach device or something. And so you should sum over all those. So this formulation of this coherent sum of incoherent amplitudes is really important. So I'll talk in the context of GluX. We have photoproduction, a photon beam coming in and interacts with the target and produces some outgoing state. And what goes on inside this blob are a bunch of indistinguishable things at some level. And then that final state X may decay. And I'll give you examples of this. So this is a short-lived resonance, say, and that resonance may decay into 2 particles. And so I'll talk about some examples of such decays where these particles are one called the eta meson and the pi meson. And the amplitudes themselves contain things that may be familiar to people with physics, these YLMs that impose a conservation of angular momentum. These are spherical harmonics. There are things like Breit-Wigner functions that describe the line shape of X and so on. And the goal is to take a big set of experimental data and then learn about what's going on internally in these blobs. What's the internal amplitude structure? Because that's really gets at the underlying physics. What's the probability that a certain exchange happens with the target, or what are the properties of the resonance X? And so to give you a very specific example, let's we can look at some actual data from GluX. So this is GluX is a polarized photon beam on a proton target. And you can sit down and try to think about all the angles that characterize such a process. So a polarized photon beam comes in and interacts with the target and produces some state X that decays. And what we would like to do in GlueX ultimately is we would like to study the spin and parity of X, and also the interaction with the target, the production of X. And to do this, there's some key things that one needs to look at, or some key variables. So the physics lives in some multidimensional space. And one of those is, say, the angle of the polarization plane. So the polarization of the photon with respect to the plane that defines the production. So the plane that contains the vector of X and P. And then when X decays, you want to look at the decay angles of X with respect to, say, some axes of quantization, Z in this picture. So, I mean, the main takeaway message is that by reconstructing this in the detector, you can reduce this down to angles that express kind of the physics of interest, and we're going to fit distributions of events in those angles to untangle the underlying physics. So that's, I think, the key message. And to give you an example of that, we can just use a simple Monte Carlo generator, no detector or anything, and just generate, according to some various physics properties, some of these angular distributions. And I think I did that in the following slides. So I assumed, say, the production with a photon of this resonance called the A2 that decays into eta pi. And we can look at, say, this angle here, and the shape of this angle tells me about the spin of the A2 and its spin projection when it's produced. And this is say, the invariant mass of the eta pi system. You see it peaks at the mass of the A2. So this is the familiar resonance shape or Breit-Wigner shape. And then these four angles on the right side are related to the polarization plane, the angle of the production with respect to the polarization plane. And they tell me a little bit about the production mechanism. And if I change properties of the production, I can change these angular distributions you can see here. And so the goal of amplitude analysis is to, in this somewhat sparsely populated multidimensional space, come up with this model of these interfering amplitudes that describes how the events populate this space. So that's what we're after. That's the idea of amplitude analysis. And then the backbone that may be familiar to many of you for doing this is the so-called method of maximum likelihood. And so I'll just review this in case this is a new idea. Actually, there are really good reviews of maximum likelihood in the PDG, just the method of maximum likelihood for parameter estimation. But the idea, right, is that you come up with some way to write down a PDF or a probability distribution function that describes the probability of observing an event subject to some parameters that you want to vary, and then you maximize the likelihood subject to those parameters, and that's how you estimate those parameters, by maximizing the likelihood. And so what you're trying to do is, given some data set of n events, you're trying to maximize the probability that you would observe that data set by varying the parameters. And so you can think of this, here's a collection of data from an experiment. Some people may recognize this data set, but there are events in all of these bins in the cystogram. And here's some blue, green, and red choices for the probability, basically, of observing this whole data set of events. And you can probably see that by making that probability peak where the data peak, you end up maximizing the joint probability, the likelihood of the data set. And I want to point out that this is distinct from chi-square fitting. So when I draw this 1D plot, your brain probably goes to like drawing the best fit line that goes to the error bars, sort of a chi-square minimization. But in maximum likelihood, you have the individual events, and there's no notion of a chi-square. You don't have to bin up the data or count events in a bin. You just need to compute the probability for every data point, and then maximize that probability for the whole data set. So that's really important in the context of amplitude analysis. And so to make this a little bit closer to what we're thinking about for amplitude analysis, here's an analogy. You can imagine, shooting particles at some screen with some slits, and then one at a time, the particles hit this detector back here, and all you do is you write down a list of the exposition of the locations of the particles. So in the end, your data set is this list of locations X where the particles hit the screen. And then you want to maybe go back and figure out what values of little d and big D there are. So maybe you're trying to measure these little d and big D. And if you did that, you would use some physics-inspired model, probably based on interference of rays, to come up with some expression like this that casts this intensity in terms of the parameters that you want to know. And then you would guess some parameters for D, little d, and big D, and you construct a PDF that was properly normalized and compute the likelihood using this list of your detected particle positions on the screen. And then you would iterate and just keep going around and around and around until you're convinced that you found the maximum of the likelihood. Now, in practice, we minimize -2 log likelihood, and the AmpTools package uses min-wee to do this minimization. So AmpTools itself is really a mechanism to formulate the likelihood and deliver it to some algorithm, which is right now min-wee, but could be other things, and then continue on and on and on. So we have to put the pieces all together a little bit, and then talk about how we're practically going to do this. So we need to construct the likelihood for a data set of n observed events, and we're going to minimize -2 log likelihood. Okay, so this is the likelihood expression that we're going to work with, and the term in front sort of, well, this is so-called extended maximum likelihood, where this is the Poisson distribution that normalizes all the various terms, and then I take the product of over all the observed events of the probability of observing them, and if I want to. This has to be a properly normalized PDF. So if I want to do that, I need to consider two things. I need to consider I, which is the intensity. That's the physics model. So this is the sum of the interfering amplitudes, and it lives in some multi-dimensional space X, and it has parameters theta that I want to figure out. And that could be couplings or masses of widths or resonances or phases. And X are like these angles that I was referring to earlier. But then there's another key term here, which is this function eta, and that's the acceptance. So the detector doesn't have perfect acceptance, and when you do the analysis, you place requirements on the reconstructed events, and those are not uniform in all those angles typically. And so there's some acceptance function for the analysis and detector. And that poses a little bit of a challenge, because in order to normalize P, I have to be able to integrate this whole thing. And I'll talk about that particular thing in a little bit. But what AmpTools does is it provides a framework really to construct this likelihood and construct this intensity I. And it does so by assuming that at the lowest level, you can always write this intensity as a incoherent sum of coherent sums, which are functions of the kinematics. And I'll avoid all the technical details, what the S's and B's are. These are fit parameters, real numbers and complex numbers related to the phases. And the amplitudes themselves that describe the event that happens, AmpTools allows them to be factorizable. And that's important because often these amplitudes have kinematical pieces that are, and then dynamical pieces, and these vary at different times and have different constraints. And so this amplitude function is a product typically of amplitudes. All right, and so this is the likelihood problem, but I want to speak a little bit about this because and also where we get to the parallelization effort and the computing aspect of it. So to properly normalize the PDF, I mentioned you have to compute this integral, but eta is not an analytic function that you write down. And so you do this by numerical integration, and so there's a relation between integrating a function and computing its average value. So the integral of a function over some region is the size of the region times the average value of the function. And think in 1D, this gets you the area under the curve. And it turns out that in likelihood minimization, it's sufficient to neglect the size of the region, because it ends up being just this constant factor or constant offset in the log likelihood. And so really the only thing that you need is the average value of the integrand here. And you can get the average value of the integrand by taking all of the events that were detected and passed all the analysis requirements. And for those events, computing the intensity. And that gives you the average value of this function. And then when you go back to the page before and take -2 logarithm of that, you can show on a sheet of paper that reduces basically to this expression. So this is the final thing that you need to try to minimize. And you're going to minimize this subject to the parameters theta. And here for this integral, we insert this sum over here. Now, the thing to point out is that this first term in the likelihood, this involves computing log of the intensity for every data event for every fit iteration, right? So you make a fit iteration, you change theta, and you just sum over, compute log I over all the data set. So here's a sum over all the data. Here's a sum over all of the accepted Monte Carlo, right? That's what's embedded in this integral. So in the worst case scenario, at every iteration of the fit, you need to evaluate your model for every event in the data set and all the events in the accepted Monte Carlo set. And so that means a few things. One, you need large RAM to park this data set if it's big, but also it provides an opportunity because every event is obviously independent. And so these sums can be parceled out and done in parallel. And that's what we do in AmpTools. So in the end, I want to show actually what you hope comes out in the end, right? This is again a peak, but this is your accepted Monte Carlo weighted by the model, and here are the actual data, and you can figure can include some background contribution, but this is a typical plot that you would see in the end that may convince you that you have a good fit to data, and there are tools to make such plots embedded in the AmpTools package, but I won't talk about that because that's not the highly parallel computing part of it. So I want to speak a little bit about parallel analysis with AmpTools. So first of all, the whole design package or design goals here was to try to optimize separate really the physics bit from the computing bit. So have this core that runs quickly and can do this sort of parallel computing and leave the bits about writing down the physics expressions and the models and all that, make that as simple as possible. So you could just take this and plug it in, and that facilitates lots of things. Makes it easier for students to use. It facilitates collaboration with theory and so on. So for AmpTools, the user provides this algorithm to unpack 4 vectors. So you're going to compute the model on all the 4 vectors. So you just need to get them in somehow. Actually, it doesn't even have to be from a file. It just, this piece of code you have to provide that gets them from somewhere and delivers them to the framework. And then you need to specify what all the physics amplitudes are and how you compute them from the 4 vectors that come in. And then as a user, you would figure out how you want to arrange these products and coherent sums and where the parameters are and those sorts of things. So this is the type of stuff that you would want to do as a user. And the goal of AmpTools is to try to provide the framework to do that doesn't make any assumptions about the experiment you're doing or about the physics model, and provide parallel core libraries that will help you do the problem efficiently. So AmpTools itself actually is just a library, and it hopefully is a modular set of classes. That was the intent, that allows you to do a variety of different things. And so I want to focus now my last 5 minutes or so really on this performance and parallelization, because that's probably what some people are quite interested in. So what drives the fit speed? So this is the expression that I mentioned before, where, as I said, in the most complex scenario, you're doing the sum over all the data and the second sum over all the Monte Carlo. And you may need to evaluate this function maybe 100 to 100,000 times. This is a pretty drastic case, 100,000 in a single fit. And large data sets may have millions of data and accepted Monte Carlo events. And also this intensity, the larger the data set gets, the more sensitivity you have to subdominant amplitudes. And so you're inclined to include, smaller and smaller effects in your model. And as those additional effects get included in the model, the cost of doing this computation is growing like something like n squared, the number of amplitudes in the model. So this whole thing really balloons in computational cost when you get to large data sets with large numbers of amplitudes, which is the case that we have in a lot of modern experiments. And so there are 2 things you can do. Obviously, one is computing this as fast as possible. And that's really what I'm going to talk about. But there's another important thing, I think, which is trying to reduce the number of times you have to compute this. And they're probably, as I mentioned, we're plugging into Minuit, but there are perhaps other minimization algorithms or other methods of maximum likelihood estimation that may reduce the number of likelihood computations. This at the moment seems like a harder problem, but if anybody has advice on that, I would be interested. So we can definitely tackle this problem of trying to compute this as fast as possible because it's a easy parallel computing. Well, not easy, but it's a feasible parallel computing program. So everything is independent, as I said. All the data in Monte Carlo are independent. So we just do the partial sums. And when we go to GPUs, also the GPU is really nice because it's very finely parallel. And so on the GPU, we're doing individual computations of amplitudes for multiple events in parallel and then storing them. So it's a fine-grained parallelization on the GPU and then do these larger computations on the CPU. And so if we were to sketch what this looks like in the most complex case where we have GPU accelerated processes, so we have GPUs distributed across a bunch of nodes, and we have this coarsely parallel layer that's implemented by MPI. So this is a spin around forever, this message passing interface. So these are individual MPI processes running on multiple nodes. And then each of them may be accelerated by doing this finely parallel GPU acceleration. Or you can omit the GPUs and run only CPUs too. So this is the picture to have in mind for the parallel computing. And then the partial sums are all collected by this lead process. And the lead process assembles the final likelihood, hands it over to Minwi, and Minwi says, here's the next set of parameters. And it delivers the parameters and computes the next likelihood. So it's just about computing the likelihood and delivering the parameters and iterating as fast as possible. There are some design challenges here. One design challenge is that you have to make user provided code run fast. So if it's code that you didn't write and you want it to run fast, that can always be a challenge. So the first step to make that happen is to not call it any more than you have to, because it may not be optimized. So there's lots of caching that happens if you don't need to call the user provided code. But then also there's some coaching that has to happen and best practices, I think, for writing user provided code. So when I say user provided, in this case, the big thing is like, how do you take the 4 vectors and compute the amplitudes from them? So that's often a function that the user will write. And so in GluX, we have a repository of these functions, and we try to edit them and make sure that they're somewhat optimized to take advantage of the framework. So this has to happen first, and then the next step is to parallelize it using MPI, but that is basically invisible to the user. Everything happens in the framework. The data distribution and everything goes on in the framework. And we chose MPI because so the big thing is really distributing the data set and doing the computation. The resources for the program itself are very light. So like multi-threading is not so useful in this case because it's not helpful to share all the resources for the software. It's much better to be able to spread the problem across a lot of nodes. And in the old days, we were really concerned about the aggregate RAM. And so spreading the load on RAM across many nodes in a cluster was important because machines didn't have quite the RAM that they have today. So that was important. On the GPU level, it gets a little bit more complicated because now you must have things like, I just put this code here. I don't expect people to read code, but you must have now a CUDA kernel. We use CUDA for the GPU acceleration, but in CUDA, you must compute the amplitudes if you're going to do this. And so this requires maintaining some GPU code that can be compiled with NVIDIA's compiler. And it has to produce the same result for, say, the Breit-Wigner, for a particular set of 4 vectors as the CPU code does, obviously, or else. So you have potential divergencies and things like that. And we've tried to make a lot of macros that make the GPU coding less error prone. So this requires a little extra layer of work. But again, if you're working in a large collaboration, it's we often have GPU accelerated versions of all of our amplitudes, and that's really handy, and share them. So performance. So let's talk a little bit about performance, and then I'll wrap up and try to answer questions. I don't want to go over too long. So performance and scaling. So this is a recent fit that we ran using some data from Best3. Actually, we didn't run. I should thank Niels, who's a postdoc in our group at Indiana. He was kind enough to try to doing some tests and benchmarking of this code. So this is a pretty extreme example. It's about 1.3 million events of the type JSI to 5KK, and it has the Monte Carlo set's 2.4 million events. So it's like 50 amplitudes and of the scale 100 free parameters. This was taking about 100,000 function calls to convergence. And on a single core, this would take about 40 days to run. So obviously that's not sustainable. You can't do any sort of research if it takes 40 days for your fit to converge or not, and then try again. And so we tested this out on, actually, IU has just commissioned a new machine to celebrate the 200th anniversary of the university, which is nice. A nice new supercomputer, Cray. And we all have access to this. It's really handy. And so we tried testing this big problem on this machine. And you can see here, this is using CPUs only with MPI acceleration. And this data point out here, so the dotted line is a linear function. So this is the best you can ever do. And this is the likelihood evaluation rate. So this is perfect, strong scaling. And this point out here is now 4,096 processes communicating across 32 nodes. And you see that's where we start to hit the limit. If we go up to 8,000 jobs, we really don't get more performance gain at that point. So there's some other probably, these AmpTools law things, there's some serial part of the code that kicks in here. And then on the GPUs, so this machine also has 64 nodes, each have 4 of these NVIDIA A100 cards. These are amazing GPUs, and there are 4 on every node. So we tried running with up to, I can't remember how many, 40 or something of these GPUs. And you see we get, decent gains. There's some funny anomalies here that involve technical issues that are probably beyond the scope of this discussion. But roughly you see there's like a factor of 2 orders of magnitude. And that's been pretty constant between the CPU and GPU improvement. So that's nice. And this is really great scaling. It's easy to get the MPI to scale pretty well. So just a few comments about, I think I said this, MPI solutions are transparent, and a single GPU is about 100 times speed gain. The GPU is complicated to implement and do it well. In our applications, they tend to be, you're limited by memory bandwidth. So it's a lot of data that you want to compute on, and the computations maybe are a little bit light for what the GPU is capable of doing. And so balancing that is tricky. And if you've written GPU code, you have to get pretty close to the hardware to do this. So you're pleased with the factor of 100, but then you run the NVIDIA profiler and you say, oh man, I can have so much more if I could just figure out how to use all the power that's on the GPU. Some things about the GPU also is that you prefer double precision for stability. So this, if you're buying hardware, this is maybe a little bit different than what you would buy for machine learning applications. I think NVIDIA is really excelling in high speed, single precision for machine learning. And you'd like large amounts of RAM for this application because you want to put big data sets in, and it requires some user development. And the whole flexible framework, it's there in AmpTools, but a one-size-fits-all optimization is challenging. Probably anybody that's optimized code knows this. So just as an example, a recent fit we were looking at in GlueX, we got a factor of 4 speed up just by better using the memory and doing some caching. But then that in turn enabled a factor of 100 going to the GPU. So it was a factor of 400 speed up. But this first step is maybe a little bit non-trivial, and you have to think about the problem a little bit and how to do it. So that is true. So there's sort of specialized solutions in the context for every problem. Okay, so last slide. Just a little bit of history. I can leave this up. So AmpTools was part of this 2007 proposal to NSF Physics at the Information Frontier. That's when we first started going, and we've been doing NVIDIA accelerated fitting for over 10 years now. And so it's just gradually evolved, and we've incrementally tried to improve the code. And big thanks to the Indiana University High Performance Computing Group for the machinery and also lots of advice. You can find the code here, and it comes with an example you can run. So I'll stop there and answer any questions people might have. I'm sorry to run a little bit long. Yes.
Maybe naive.
Yeah.
When you're describing your algorithm, it reminds me really of what machine learning people do with stochastic gradient descents, where you have large data sets, you're trying to get a maximum likelihood. Have you looked at the tools that are developed in that world? Because they have huge tools for going parallel, multiple different architectures, and there's a lot available in the machine learning community of just kind of ready-made tools. And I don't know if you're going to get anywhere near the same performance as you're seeing with your more specialized tool. But I just was wondering if this is something that you've looked into.
No, I haven't. it seems difficult to give up. I mean, there's some layer of organizing all of these computations that are really, specific to amplitude analysis, using complex numbers in all the right places and all that. So there may be good ready-made tools for the layer between that computation of the likelihood and how you iterate, perhaps. But no, I'm not familiar with what's available there.
Well, it might pay looking into it, because that's a very, very large scale effort. I mean, whatever you're doing is completely dwarfed with the kinds of computations they manage, and there's a very large variety of computations. So there are other computations that are really complex that are used in those communities. So it might be worth sort of piggyback on some of that technology.
I believe Marcus has his hand raised.
Thank you very much for the talk. I think this is an excellent example where science and computing meet, because the more computing you have, the more science you can do. If I have understood your science and case and talk correctly, then you look for a specific, let's say, exotic meson, and you have some theory from the Monte Carlo how this would look like, and then you look if you can find this in the data. But could you, if you would have enormous amount of computing power available, also turn this around and scan systematically the amplitude space which you have, and see what possible resonances could be there, and then make a dedicated search for that?
I think, well, we sort of do that latter thing that you suggest. So our goal is we don't look for one specific thing using this technique. Our strategy is to completely describe how a certain reaction proceeds according to these underlying things. So when I draw a picture like this in the top, X can be any number of many things with many different spin projections and angular momentum and everything. And so we have to describe the entire data set that populates some final state A and B. So what we see in the detector is gamma P goes to A, B, P. And so we need to describe everything that does that. And one of those things that may happen is one of these exotic amplitudes. So we're sort of trying to do this searching of all possible physics. And so this is a challenge, obviously, to figure out which parts are significant and which are not significant, and what the simplest explanation is for some distribution of data in the space of angles.
And to what extent do you depend on theory that someone calculated, oh, this resonances could be here, there, or you're more or less really model independent with this approach?
That varies, and it depends on the strategy. So there's some theory that's sacred, like conservation of angular momentum, and obviously, that may be challenging to implement, and parity constraints and all that, but that's not going to be violated. We can. The balance of going completely model independent is that often what you extract then doesn't have any direct interpretation, because what you really want to know about are things like, where's the pole in the complex plane and the coupling of this pole, because that tells you the property of a resonance. And you don't care about what's the amplitude and phase of the spin 2 wave at some particular bin of mass. So you can do that, but then there must be some higher level interpretation that says something about the resonances. And I think where you draw that line between how much of that theory you build into the model to the data, and how much you do kind of after the fact, after you've done some model independent extraction of some observables from the data, is a bit a matter of taste and optimization. AmpTools was designed to be able to do everything. I mean, before, these theory models were very, you didn't have the ability to compute them, on the fly and integrate the acceptance and do all that sort of thing. And so what the additional computational power has really enabled is it's enabled us to build more sophisticated theory into the fitting and apply it directly to the data, rather than trying to, distill some experiment independent set of numbers from the data and then apply theory to that number, and propagate errors and correlations of errors and everything through. So
Thank you. That's
yeah.
very interesting.
Okay, don't see any other questions. So thanks, Matthew, for the nice talk. And I believe the next speaker for today is Lorenzo Moneta, who is a long-term member of the root team at CERN, involved with a lot of the mathematical and statistical libraries in root. Can you share your screen? He's going to be talking about the future of data analysis according to root. Does Matthew have to stop sharing?
So, yes, hello. So good afternoon. So everybody says, Matthew, stop sharing. I can start sharing.
yeah, that's right. I'm trying to get the window. I can't get the Zoom window to go away here.
Let me see. Stop sharing.
Thank you. Sorry about that.
Sorry about that.
Okay. Okay, great. Thank you. Can you see the screen now?
Yes.
Let me put full screen. Okay, great. Thank you. So good afternoon, good morning, everybody. So thank you for this invitation to give this presentation on the future of the analysis, in particular, what is the root view of the analysis, how root will evolve in the future for data analysis in high energy physics. So I'll give you basically the outline of my presentation is the following. I'll give you a bit of, after the introduction of root, I will describe basically few major things that we're developing root in the future for analysis. One is developments in the I/O. In particular, I will describe what is our new data structure that we store in the RENTOPA, which will be the tree successor. Then I will present you how we do in data exploration or declarative analysis root with our data frame. I will say some words about machine learning. How can we view the view of interoperability and how we can integrate also machine learning together in analysis, and then present you what you're doing in root, in particular in terms of the fast evaluation of machine learning models. And then at the end, I will describe also our more related maybe to the talk that was presented before, how we do statistical analysis and modeling, which is our tools for doing that refit, and how we evolve in refit for the future of analysis. So we describe a bit what you have in root now, what are the major latest developments, and also how we are going to plan for the future and what are our future development in these things. I have to say that lots of material has been presented also recently this week at the ICEP conference in Bologna, and you can see also the presentation according looking at that link. You have a link to the computing session of ICEP where there have been presentations.
Lorenzo?
Yes.
Sorry, should we still be seeing the title slide? At least I'm still seeing the title.
Okay, I see that, yeah, there's a problem with the sharing. Let me stop and starting again. Yes. It's a bit weird. I don't.
Can you try advancing
now?
Can you try advancing the slide?
Yes.
Because we see the title slide.
Yeah, no luck.
Okay, maybe because
Maybe it doesn't like this. Maybe it doesn't like this play mode.
Yeah, let me try something else to share. Yes, from the stop. Yeah, let me try with sharing the PDF. Sorry for this problem. What is it? It's a share. No, that's no work. Don't understand. Why leave like it? If, maybe don't do in play mode in full screen, and I will share just.
Yeah, maybe.
Yes. Good. Is it visible now?
Yes, we see.
We see,
Second
okay, you
slide.
can see the slides, yes, exactly. So I was saying exactly that we show exactly different components of root, like the rentupler, data frame, the machine learning, then RoofIt. And I will look at it, show the recent development of these tools and also the future plans. So that was introduction. So Root is an open source, a community-driven project. And despite existing for many years, you see that exactly right in the figure like below, that has been very active. There are lots of people which are contributing, particularly with many external people. So it's an open source project, everybody can contribute. And this number of contributors is increasing with the time. In addition, as everybody knows, it's used by basically all app experiment. We have more than 1 exabyte of data we just on Root. So the basic components is that we do in particular to analysis the part of I/O that we need to be read and writing data very efficiently. Having interface for analysis like histograms or data frame to make filtering and declarative analysis. Then we have interactivity, which is fundamental, and we have the C++ interpret Cling, and we also provide the binding to Python. Then we have mathematical library, which is needed for mathematical functions evaluation, but also for random number generation, numerical algorithm like minimization, like min, which was mentioned in the talk before. Then we have statistical and modeling that is used for fitting and to build the final statistical analysis of your data. Then the graphics for visualization, and then also machine learning, where we do in particular, we focus on model evaluation and also interoperability, because we have many tools developed for machine learning outside also energy physics. So we show some recent development in some of these tools. Let me start with the rentupler. So the rentupler is a success of T3, which is based on experience of more than 25 years of TT3, and the schedule so to have this production of a rentupler for high luminosity LHC. And the idea is to redesign the system to be much more efficient, in particular to provide less disk usage, which means also a saving in cost, and also to be more efficient in terms of CPU when you're trying to read the data in particular. And so that's a result. At the end, the result that you see, we'll see in the benchmark, we have 25% smaller files compared to T3, and also a factor of 2 up to 5 better single core performance when reading the data. And this, in addition to that, is not only that, it's a more robust system. We will have better using of exception to prevent I/O errors. And we have better support for modern hardware, things like object stores or cloud storage with better support. And also we have built-in multi-threading, which allows also to this faster performance. So just some comparison, I mentioned before, not only to TT3, but also to the competition of different file storage format. We see that it's faster than TT3, but also faster than the Parquet from Apache Arrow, or for things like HDF5, both in row and column format. And not only that, this was the size of the disk, so it's smaller the size with the rentupler compared to these other storages. But in addition to that, it's also faster in terms of reading. When you're reading, for example, in the case of some typical LHC analysis, like in the case of X for lepton from CMS, or a B analysis from LHCb, where you're reading some part of all the branches of the tree, you see that the rentupler is a factor of almost factor of 5 faster than DT3, but also faster than Parquet or HDF5. It's particularly much faster than the HDF5. And in both typical use case, so that we are reaching is a better performance. So what are the plans? The plans is to deploy then a rentupler for a luminosity LHC. At the moment is in the experimental phase, so we probably will have system format in the disk of the files in order to finalize it before when it will be freeze, and then all the old format will need to be supported. And at the moment, so we're happy to get any feedback or criticism before when we go into the production phase, which is expected to happen around the long shutdown 3 after run 3 of LHC in order to be ready for the high luminosity LHC, which should start in 2029. If you have any question every moment, please interrupt me and I can answer, otherwise we can do that later. So after AmpTools, I wanted to describe a bit more the analysis part, in particular their data frame. So in analysis, we have a different landscape, which starts from the life cycle, from producing the data, having a first exploration of this data. And then you want to do some systematic analysis, some scale out, some really production of your analysis in order then you produce the final data that you send to a statistical tools in order to perform your measurement, like could be measurement of certain parameter, could be the mass of the X, for example, and then measure of significance of a particle is discovered, etc. Then you want to run the analysis on different platforms, not only on your laptop, but also a multi-core machine on a cluster, or on a cluster where you want to submit jobs. So you have a different environment, a different way where you run an analysis. In addition, the language is not only C++, but you have a mixture basically between C++ and Python, where C++ maybe is decreasing analysis and Python is increasing, but then not one is disappearing. And for the storage, we need to run not only on the local disk, but also on this network storage, on the cloud storage like EOS or something else like. And their data frame focus in particular gives you a really flexibility to run all these different parts of the analysis. In addition, so allows start from the production for this AmpTools to this quick exploration to allow, for example, to make some quick histogram to understand how you want to focalize in your analysis, and then to run all your systematic analysis and scale out. And then we'll send the data, as mentioned before, for the statistics, which will be described in the following tools. In addition, works also data frame on a different time, on both in C++ and Python. So depending on the user, one can choose which language to use. Let me show a simple example of how their data frame works. So you have a simple example of code where you provide an input data, which could be a root tree, but could be also some CSV files, some text file, whatever, could be even Apache Arrows format, could be a NumPy array, we'll see later. And then you filter this data, for example, performing some event selection, you can derive some quantity, you can aggregate this data in an histogram, and then produce also a copy of this data in a file, like in a root tree, in another root tree or AmpTools, where you can go into store and use it later. So basically, the field just describe the different analysis ingredients and run out all the technicality of all this step on the analysis. And all the event loop also is guaranteed done by your data frame in order to have maximum efficiency. And in particular, if you want to switch to multi-thread execution, it's very simple. You just need to add one line where you enable the implicit multi-threaded route, and reanalyze you run in parallel, depending on the thread of your machine. And if you want to run, for example, in a cluster, we have also this capability to do distributed execution in a cluster using the Python and connecting, for example, to a Condor via Dask, a Condor cluster, or you can run different types of cluster execution on different type of machine. And in particular, you have all the merging transparency for your results, and you will get like running a single node. This describe you is distributed data frame, and which allow you see in the plot on the right that you have a very good scaling, both when you run on, for example, on Dask or on Spark cluster, you have a very good performance, almost close to the ideal speed up that you would expect if you would run completely parallel. Just another word on the performance for the data frame, which allows us, for example, to show that the data frame performs much better than all the competition. For example, this was some studies which was done by the independent team, showing that running the data frame was faster than other commercial tools. And in particular, also, if you would run on a cluster of a commercial cloud, you will also be cheaper because we would use less cheap CPU. This is another benchmark, for example, when you compare a data frame with the Coffee, which is another solution developed by App, and you see that also in that case, the queries of their data frame are faster than the one or the other package. In addition to that, not only you can select single events, but you can work well with collections, which data which are not flat tables, but they are really like typical in case of energy physics. We have collections data which vary event by event. And we have also the capability of dealing that inside with the data frame using what is called RVEC, which is a vector structure. It allows also to define, for example, in this case, you can define a new column PT, which will contain all PT of the neurons, which have a certain value of eta. and a certain value of the PT, and we return you a collection of these neurons and produce, for example, an histogram. You can produce easily an histogram with that. Furthermore, one other new functionality which has been added recently is the capability of doing systematic variation. And this is called what is called this function called vary. And you basically define how you want to vary compared to that variable. You can vary, for example, you have variation up and down, and automatically you proceed, you do the analysis as usual, and you don't have to run the loops on your event loop all the time. In a single event loop, you can compute all the histogram variations, which contains the variation up and down, for example, your particular variable. So these are allowed to be very efficient, and you can produce all these histogram in a very efficient way and study all your systematics. In addition, you can run as before in multi-thread and also distributed. Another important thing to mention about our data frame is the capability of interoperability. We can, for example, export data from the data frame directly to NumPy. So by for example, selecting a certain selection, and then you call the function as NumPy, you're going to select to output a dictionary of NumPy array containing the values of the column X and the column Y in that case. And you can also have the opposite. From NumPy, you can create a data frame where you can do analysis. And this work in progress for transforming a data frame to Awkward array. See the link, for example, here. And also we are working on doing a batch computation of this data frame, which is useful to generate batches, which will be useful to feed machine learning models. I will mention this later, and this will allow us to integrate better with external machine learning tools. So in conclusion, for the data frame, we have lots of new features, lots of things, in particular, integration with the REN tuple for the I/O, which is to be very efficient. Also, we want to integrate better with machine learning method. I will mention that later in the next slides. And also, one important thing to do is that we are keeping evolving, and we want to also, we need your feedback in order to focalize on the right features in order to be ready for the analysis needs for the luminosity LHC. So now moving to the part of the machine learning. As I mentioned before, you can, given a data frame, you can also evaluate machine learning models directly in the event loop of the analysis. And this thanks to new tools which has been developed recently, which is called SOPHI, which allow to take whatever machine learning model been trained by either TensorFlow or PyTorch, which are basically the two standard tools for training machine learning models, which are developed outside energy physics. And they can be stored in a standard for the models called ONX. And from that standard, we can read these models and generate C++ code, which is a minimal dependency, can be easily used in whatever C++ framework or analysis. In particular, can be integrated, for example, with a data frame sequence of operations. So in the case of exactly this integration with the data frame, we have developed a functor which allow to inject this evaluation of the machine learning model directly in the event loop. And for example, in this case, you want to evaluate a model which takes as input 7 columns of your data. You specify which are these columns. You specify so the name of the model that you're reading from your files. And then you can specify also the number of slots. So how much in parallel you want to run your evaluation. And then you can create an histogram which contains the result of the evaluation of the model. We have a full example of this code in this linked tutorial, for example. This allows to really integrate this machine learning evaluation in the model. Some words of SOPHI allows exactly to parse many types of different models. We have a sort of operator, so we are expanding the support, adding more and more operators according to this standard. In particular, we are also focusing now to try to allow for operators which allows us to, for example, parse models like graph neural network, which are more and more used in energy physics. At the moment, we parse, for example, basically all the standard dense convolutional and recurrent models. In terms of performance, also we are almost faster in some cases than for example, the competitor on X runtime, which is a commercial tool developed by Microsoft, but require much more dependency, more difficulty to use and integrate with tools like our data frame or other whatever C++ code. And in that way. So we are also in, as you see, for example, in this benchmark, you see that when you use a data frame with this for a normal standard dense model, you are factor of 2 faster than using an X runtime or another tool which was developed in the context of Atlas, which was called LWTNN. As for the machine learning model, we can also do fast evaluation also for the big boosted decision trees. We are a tool called RBDT, which can read, for example, XGBoost files and can, in a similar way as I described before for the neural network, can evaluate directly your machine learning model. It can be also integrated with their data frame. So in addition, within the machine learning route in TMVA, we are working a lot on this interoperability between different tools. We are moving also all the TMVA interface to be more Pythonic. So from a string API, for example, we are moving to Python keywords arguments, which allows that to be more Pythonic and better usage in Python, since many of the people of machine learning are all using Python. Then we are also we are now personally allowing of using, for example, scikit-learn, Keras, or PyTorch directly in the TMVA workflow. Like in this example, you can compare different TMVA tools and external tools in the same context and make a comparison in terms of performance or for classification, for example. And then one of the future things we are aiming to work is to develop a generic data loader for machine learning workflow, which allows, for example, to read the data which will not fit in memory, so a large amount of data. You build a generator which is directly connected to the root IO, allowed to create batches which can then send to machine learning tools to train. And in particular, we want to feed directly the data from the disk to GPU to have the maximum efficiency and minimizing the copy. And so these are working, that is a work in progress. And we'll probably have more news on that later in the year. Now, I don't know how much time I have still left. I will continue. So talking the last one of the items I wanted to speak about is statistical modeling. And in this case, so we have seen for analysis that it's important. We have this event selection, the definition of the final data set, which is using this filtering and first pass through the analysis. Then we are at the end, given a set of data, we want to do some statistical analysis in order to, for example, measuring parameter or doing physical studies, like, for example, combination for the X measurements, like the mass or the cross-section, or doing effective field theory interpretation, etc. And many of these operations require to deal with models which are much more complicated as we go higher in complexity, in particular through without LHC, because we combine several number of analyses. So the number of parameters when you do dimensionalization becomes very large, in the order of 1,000. We have hundreds of likely components and 100 data sets. And then we have only one tool basically capable of handling such complexity, a different heterogeneous model, which is OnFit. And the tool was, in recent time, we've really been developing and bringing up the evolution of that tool to improve the capability. And in particular, I will show you, we can really speed up also these tools to really, the aim is to go from a fitting, which takes basically 1 day, to the time for a coffee. So that really will increase the productivity of the physicists very much in that case. So fit is evolving in very different areas. And we have seen, we'll see now that we are working on different things in order to improve the performance. Things, for example, parallelize integrated computation, implementing vectorization, porting some of the code to GPU. And one other aspect is also use automatic differentiation, which would allow also a performance boost. In addition to that, we improve the usability, for example, adding Pythonic interface to better usage of the tool in Python. Let me do some words about this. One of the first things is gradient parallelization. This was just presented at the conference last week. And this allows exactly this gradient parallelization, allow to speed up, especially fit where you have a very different type of a lot of different type of components. And the idea is when you're doing such a fit, you will need to compute each single partial derivative of your model. And model which contain 1,000 parameters, so you need to compute of the order of 1,000 partial derivatives, and each derivative requires something like of the order of 2 evaluation of the likely function. And then the idea is exactly to run all this gradient evaluation in parallel, And then when you have a work scaling algorithm, you can then automatically the balance of this, even if the different components take a different amount of time, they will balance with each other. And in fact, you see that in this way, we can reach quite a good scaling, and we can reduce the CPU time. For example, in the case of this machine with 16 cores, we can decrease the CPU time in this X combination fit from 2 hours to something like 30 minutes. In addition to that, we can also combine with a different type of performance improvement, which will come from the vectorization and the porting to GPU. First of all, so we have been redesigned the way of evaluating the model in RuFit. We have been moving from an event-by-event evaluation of the model to what we call a batch evaluation. So basically, each computational graph, so each single function will not evaluate one single event, but will evaluate a batch of events for the dataset, like it's happened, for example, when you do in machine learning models. In this way, you group the computation together, and you have speed up not only by vectorization, but also better CPU caching. And then, one additional things you can do easily when you're doing that, you can also add the multi-threaded support to split the computation of different nodes independently, and you can also port in some of the computation to GPU. And you see that, for example, in simple fit, you can get speed up by using 24 threads of the order of 10 by using multi-thread or by using GPU computation. But also just worth mentioning that just using this batch mode for all the different types, basically, of the tests that we have in RuFit, we can get a speed up which is larger than 1 by using this batch mode evaluation. And then if we combine what we have, we combine with that parallelization of the gradient, we can really reach a large factor that we can allow us to reduce significantly these complex fits. In addition to that, we are working on doing this Pythonization. So we're trying to make more Pythonic the interface or you interact with RuFit. So before, for example, you will need to create lots of C++ objects also in Python, which are not really needed, for example, because you can use some native Python, for example, list or collections without going to this C++ RuFit objects. This allows a much better interface and easier way of driving your fits directly in the analysis using Python. This is an example, for example, a tutorial that you can has been transformed from in Python and can be in a very looking the code could look much better and much simpler. Similar things, so we have also converted, we can use NumPy arrays. So for example, we can convert directly the data set of using RuFit from NumPy into NumPy and also to pandas. And this allows exactly to also interoperate better with different tools. One thing also mentioned for RuFit is that the fact that we are aiming to have in the future auto differentiation. Auto differentiation, so is tools which allow to compute automatically the gradient looking at the computational graph. So are you doing when you're evaluating a function, you will have a computational graph and your computer can examine this computational graph. And then from that, compute automatically using the chain rule of derivation, the gradient function. This is possible thanks to a tool called CLAD, similar to Kling, which interprets the C++ code and automatically can generate the corresponding gradient function. And this is already integrated in existing root entity formula class. And if we deploy this, for example, for the fitting root, which is already there, it's possible, you already have a large speed up when you're doing a simple fitting root, like for example, the histogram fit. When you go to a large number of parameters, you see that you have a speed up of around a factor of 10 when you use it, for example, this CLAD automatic differentiation with respect to the standard numerical differentiation, which is used in the default case. And we are working now to integrate also, because for the fitting, we need often also to compute the covariance matrix of the fit for where we derive the parameter uncertainties. And this requires to compute the second derivative, so the Hessian of your likelihood function. And we could compute this Hessian also using the automatic differentiation, and would allow also for another speed up or larger speed up in the case of large number of parameters. And we need to integrate that now in Inuit. And the idea is to deploy this automatic differentiation also on RuFit to allow for a speed up in addition to what we have done now. It's completely orthogonal for what I described before due to virtualization and GPU. And we started, for example, with a prototype implementation in the case of models, binned fits or templated fits, which are based on this factory, which is a standard type of model, so we can know the models well. And in that case, it will be easy to parse this full model and send to cloud, which can automatically compute the gradients. So that's, I think, is my last slide for the tools and bring me to the summary of my presentation. So I'll show you that the feature analysis app, so basically what we have now in root, we should fulfill the requirement for feature analysis app, which would be to be efficient, to have simple interface, to be reliable, to be supported, and to have a good interoperability with different other tools, not only within energy physics, in particular with tools which are developed in Python, which are more and more common. And so what is evolving exactly in order to fulfill these requirements? And we have a large effort from the whole team in doing that, but we need also your help and especially user help for the continuous feedback and support in order to have then the right tools for the luminous LHC and for the future of the data analysis app. So I conclude with some reference in case you mentioned before the chat presentation, but we also need to put a link to the latest root user workshop, which was happening in May at Fabula, which are maybe some more interesting presentation about the evolution and of root. So I'm open and hope I did not took too much time, and I'm open now to any questions.
Thank you, Lorenzo. Do we have any hands raised? Michael.
Hi, thank you for this very nice overview. It's interesting to hear what's coming up, and especially the long time scale you have foreseen for the RN tuple. I just had a quick question about our data frame. You talked a bit about its speed compared to other things. So analysts working in Python who are using PyRoot, the obvious alternative would be a pandas data frame, which made an appearance later in the talk. I was curious if you had any info on benchmarking of our data frame versus pandas data frame in terms of speed.
I don't have actually that number, so I think has been done in the past, but the functionality is a bit different, yes, but I don't have the exact this number now, and I don't know, but with something I could ask exactly to the really developer for data frame eventually to produce something in case you're interested, or if he's already done this benchmark in the past.
Yeah, no, I partly asked. There's been a lot of buzz of sort of the Python tools for HEP community lately, and it would be interesting to have some concrete numbers.
Sure, yes.
Yeah. Thanks.
Okay, nobody else. What you mentioned, RN tuple was like a few years out from finalizing, and is roof. And then you mentioned lots of ongoing developments in roofit, vectorization, and optimization, et cetera. Is that some sort of a similar time scale? Roofit, few years type development?
No, I think the RN tuple, yes, it's just we require some time to finalize in the sense that we want to be sure exactly, because once we finalize, we cannot change anymore because it's the IO part, so it takes a bit longer, and we need to support for all the full lifetime for many years. So that's but it's still usable now. Just now at the moment there could be maybe some small changes, and the backward compatibility can be maybe not fully guaranteed as will be in a few years. For the case of roofit, no, the developments are happening basically now. So all what we present is basically already available in the latest version in the master or the 6.26 version of root. The only thing is not yet available is the integration with auto differentiation. And that will, we should probably come hopefully for the next release. If not, they will come maybe the one later. But we are planning to do for the 6.28 release, so end of the year, to have some preliminary support, first support for auto differentiation. And also we want to integrate, in the case of roofit, both the parallelization of the gradients that they show and the batch computation, which at the moment are a bit separate, but they should be integrated and combined together also in the next release version.
Okay. Okay, thank you very much, Lorenzo. I don't see any other hands raised.
Thank you.
So I think we can move to our final presentation. Oksana Shadura, also from CERN, looks like most recently architecting systems for an interactive HEP data analysis facility, including distributed systems and data delivery, and is going to tell us about a recent analysis ecosystems workshop. So I guess we're, unfortunately, probably my fault a little bit over time, but hopefully people can stay.
Thank you for your introduction. Yeah. So you hear me, you see my slides, right?
Yep, everything's good.
Yeah, so I wanted to present a short overview of report from Analysis Ecosystem Workshop that happened in Paris basically a couple of months ago. Oops. It was a hybrid workshop. Basically, it's probably first time that after COVID, we managed all to meet together. We had 70 participants in person. You could see here a link to workshop agenda if you would like to see. 70 participants, it's because probably we were limited by the capacity in that time. We couldn't be more than 100 people in particular room, but it was, yeah, a lot of people basically. If to go through history, analysis, so 5 years ago, there was a first analysis ecosystem workshop. It was organized in Amsterdam. And main idea in the time was to check, to examine analysis ecosystem, which was in that moment, and try to predict or try to understand what will be in the future within 5-10 years. And the main topics were to check how is going to be evolution of root ecosystem, what is other developments on analysis tool landscapes, try to connect to other sciences, for example. And Graham nicely basically tried to find the conclusion of that workshop, that putting these 5 main points about criticality. In the time we were thinking criticality of better connecting root to Python, that C++ will persist, that there is no competitors in the time and performance front. Modularity is very important for all software framework, that containers could help with isolating from underlying operation system. And then was also trying to define, idea was to define golden metrics, such as event throughput, but as well latency for interactive analysis and event file size for storages. I will not go through a review of the current status. I will go maybe more about the topics that we were discussing and what were the key ideas, key points that we thought would be interested to talk again in 5 years. So this workshop, so the version number 2 was basically divided in 6 parts about analysis facility, machine learning and auto-differentiable workflows, reduced data formats, user experience, declarative languages, metadata is systematics, and real-time trigger and analysis. I would like to point you a bit about the program and particularity of this workshop, that we had some presentations, but as well we had a lot of time for discussions. And basically it was 3 days of a bit of talks and discussions, which created this atmosphere where everybody was basically trying to brainstorm what will be next for us. I will start from analysis facility as something very close to me. So here's a nice slide showing basically a comparison what was happening in Amsterdam 2017. In the times there was no really anything concrete about facilities. There was just an ideas how they should look like, should be flexible, dynamic and declarative. And now actually, as you see from the side of Rob, a lot of facilities starting to materialize, particularly new prototypes, new interesting solutions. And there is already some commonalities that basically some elements that is defined as something as a kind of like baseline, like bricks, building bricks for these facilities. About defining service platform, having clustered storage, how will look like analysis processing, to have faster WAN and faster LAN for delivery and data delivery and access, explore caches, how we will resolve situation with interactive services, and adding more accelerators for ML and integrating there. There was also interesting point that instead of focusing all the time about technical part of analysis facility, it's interesting to take a look what actually users see from the user perspective. And there was interesting presentation by Nick Smith, where basically what we could say now that we were focused last 5 years a lot on what is fast, and it seems to be not any more bottleneck. So now we need to try to make things much more easier, much more usable, much more kind of like friendly for the users. There was also other kind of component that moves a lot to make analysis facility developed much more faster in recent years is DOMA evolution. So there was identified a list of interesting kind of initiatives that were revised during DOMA activities in recent years, about network, about caches, try to hide latency, use, for example, diskless sites. There was trials about storages, how we deploy storages, what is operation models, access protocols, trying to add new authentication, such as a token, trying to explore different storage types, again, data formats, how it will look like data transformation, and what is actually data delivery, concept of data lake, and basically how all this like list, how it is related to analysis facility. We suspect that modern analysis facility will try to explore maximum these concepts so they could optimize data access and adjust to already new workflows to start to prepare for workflows that will be used run 3, run 4. The other interesting point, of course, that we need to take in consideration that we need to take into account that developers are starting to use more and more Kubernetes. As you see here is the recent numbers from Cloud Native Computing Foundation questionnaire. And it looks like we need to start to also integrate it in our facilities, but as well, there is more services developed which are running on Kubernetes. So something to take a look into. The highlights from analysis facilities discussion, there was really a lot of points. I just took a couple of them just to show you what we were talking about. That idea is that early testing is a pretty good approach, and it shows that we all should start to look more when we develop our frameworks, how we can already start to propose it through the analysis facility, for example. There is also was good point that we need to work together with the analysis framework developers to get better user experience. A lot of discussions about how we can share better environment for the users, and also to have reproducible installations for analysis facility. It's a bit different point, but of course it is important that we can reuse some development instead of duplicating efforts again and again. We were looking into the new way how we can actually test scalability, for example, and it was proposal to use Analysis Grand Challenge. It's organized by RISHub to test scalability of analysis facilities and as well data lakes. And to think about better about F-related metrics, because it's important for us to understand what the users are doing on facility. So they're working to understand if analysis is performant enough, how is user sources, users are satisfied, if we're kind of like to measure more from the point of view if the project was successful or not. All these topics we are planning to follow up on HSF Analysis Facility Forum, so you can click if you're interested, or if you're interested, you can join meetings that are scheduled bi-weekly. Next topic is machine learning. Here was a lot of interesting discussions. I will start probably with the big issues and proposals. So there was an idea that we probably should start to look more as a high energy physics community into foundation models. It's basically a #1 advancement in machine learning in the industry, and we still like not using it. What at the end, how I understood is that model are kind of trained with many kind of components, parameters, and they have like a possibility to for example, nicely to show some degree of generalization. For example, here you could see on the image, you have a text and it's like nicely basically generating images from the string, images describing this text. So this is something that probably could be a good industry collaboration point. There is no experience, as I understood, in high energy physics until now. So it's some kind of like big issue that is envisioned by machine learning community. The other part is differentiable programming. And the problem is that, is it worth it? Should we try it? How it's compared to existing methods? So other questions like, can it scale? So the idea is to try to find some toy problem with some kind of degree of realism to what is exist, and try to evaluate better how it is integrated, how it works. Other thing is that machine learning community would like to have better understanding to some common and realistic benchmarks. This is something that Lucas and Nathan presented as something that is missing, as well as better tracking of commonalities in experiments, for example, using tools and try to have like to see how we can learn from each other. From the point of view of platforms, there is a lot of ongoing efforts how to provide a nice kind of facility which is machine learning dedicated, and was highlighted the idea of ml.cern.ch, which is Jupyter entry point with GPUs and Kubeflow, and you can kind of track training workflows or ML flow, and you can even integrate with VS Code front end. So like absolutely something very how to say nice for developers. From the user experience and declarative language track, this is, I think, very nice slide that basically summarize all pain points in the user analysis user experience. So first one is systematics, then metadata, and then scale out. I will go through systematics and metadata probably later because it's also a separate track. With scale out, it's interesting because there is like, we need to try to understand differences between prototyping and actually real scale out, how users see it, different implementation at different sites, and as well consistent, again, the problem of consistent environment across all resources. Alexandra and Jonas tried to identify some key points for the problem of interoperability. So let's say histograms is some kind of key area that require some improving interoperability, as well Python bindings. There is a high demand for the general statistic model format for based like on JSON. And as well, since now we start to talk more about columnar analysis and columns, there was kind of idea how we can reach also data interoperability at the level of columns as well in the memory. What is from the user experience looks like better future is more automatic like graph-based optimizations. So users can focus more on physics instead of like trying to optimize. Trying to factor out like libraries that we have now, frameworks in more mini frameworks, mini libraries, to make them more portable, easy installable, more documentation and learning materials. Yeah, the next interesting topic we were talking about is reduced data formats. Here I focused only on Atlas and CMS, just quickly a review because I believe I'm also running out of the time. But yeah, the interesting point is that these two experiments that shows how looks like reduced formats for them, it looks like they're moving the same direction, and there is plans to aim to use, for example, fees in run 3 for 80% and fees light, which is more AmpTools style in run 4, and sorry, AmpTools style. And the idea is even try to reduce more data formats by dropping variables needed for systematics. So the idea is just to learn if Atlas could learn something from CMS where the systematics are parameterized, and as well plans to move for both formats for fees and fees light to AmpTools to facilitate columnar analysis. From CMS, in this current status, MiniID and NanoD already serve 85% of all current analysis, but there is a lot of interest try to, for example, explore such ideas like to avoid full copy overlaps, full copy of data files between data overlaps by central services, to allow people like to write, like have more modular mini ID, nano IDs like Lego ID, and as well to check out object stores and try to avoid copying columns through the all processing tiers. From metadata systematics part, there was a presented a white paper, and was suggested steps that to do, because it's a really big problem currently. So the idea is to start with some use cases, try to figure out, like, just find out which problems should be addressed, and then try to convert like on some kind of like some commonalities and so a lot of you can go through the, I think here I put the link, you can see also the link to this white paper. The interesting part that there is already some vision, and as you see everything here, which is colorful, it's what exists currently, and green parts is something that kind of deliverables, something that the work group is expecting, and also high energy physics community is expecting to start to look in like common API for the systematic providers between all experiments, across experiments, systematic as well. So these two parts, and try to optimize event processing in this case. For real trigger analysis, was a very nice presentation by Katerina. And the main statement was that so LHC challenged too much data and too few resources. So the proposal is to try to do analysis in real time on the trigger system. It's already happening. So there is in these 4 experiments, you could see there is a lot of efforts. The idea is that you could try, instead of just recording data in store, and then after reconstruct and analyze it, you do this in kind of like semi-real-time way. So you reconstruct and analyze data as soon as you kind of read it out, and then just small fraction need to be stored. Of course, there is a lot of questions here, and if you look on the presentation as well, there is a lot of questions. So it looks very, how to say, complex topic. But what was interesting is trying to understand actually if we need to build analysis ecosystem based on like constrained resources, what kind of, how it will look like for high-lumen LHC and beyond. And there was a lot of interesting ideas about so it's probably my last slide. Almost other interesting part was that on Birds of Feather session, we had like trying to define the steps of analysis workflow, but more like in to have it more in generic way, and as well try to make it more understandable even for like people who doesn't do analysis, like for example, computer scientists, which was very useful for me. And this is something interesting. So if you would like to take a look, there is a lot of nice schemas, drawings, and it could be used for better understanding how it looks like could be typical analysis pipeline, or for example, if you're working on designing benchmarks, it's something interesting to take a look. So what is the next steps is community white paper. So since we had a lot of time for discussions about missing features of future plans, now we're working on the report. You could click on it and check it out. It's still probably like almost ready, but still last remarks, last comments. And yeah, an idea is to try to document what is needed in the next 5 years, how we can improve or what we can do new. And also, like, previous report is available on Zenodo, so you could take a look and compare what is basically was happening in the last 5 years and what we think will be interesting for next analysis ecosystem workshop in 5 years. So yeah, it's everything from my side. Any questions?
Thank you, Oksana. Marcus.
Thank you very much, Oksana. This was a very comprehensive and very interesting summary of the workshop. I'm very interested in user-centered design and user experience. Have you discussed at the workshop strategies for how analysis could be made easier with facilities and analysis environments? I mean, it's one thing to say make it easier, but it's a very complex topic because for a lot of people, what is an easy analysis looks completely different.
Yeah, so yeah, it's a really interesting topic. I think there is like multiple ways how you can approach it. So first one is that we need probably to work more with analysis frameworks in the terms of like integrating how it looks like features that it was presented, for example, by Lorenzo, or from the Python ecosystem that is as well developing now, how to make it as much as possible less painful for the users. And it probably will require some data collection, like surveys from the users. So we will try to understand better what physicists are expecting from us from this point. Other thing is that since we have now chance actually to try to introduce new workflows, we need to try to understand what is actually was from the historical point of view, what was some kind of like complex issues that users were facing, for example, data handling, or like how to organize better data delivery, how to optimize storage usage, if we need to. So all these points, there is, if I will try to go through them, it probably will be a couple of pages. But yeah, at the end, what we expect is better testing. So I believe we need to do, as I told, early enough testing. So try to integrate new features directly in facilities, and try to invite your alpha beta users to test them and give a feedback. As well, try to so all I hope, from my personal point of view, I hope all these approaches will help iteratively improve average user experience.
Thank you. I have a second question. So at the end of your talk, you talked about what common problems right now are, like the metadata, and you also mentioned systematics. But what do you exactly mean here by systematics? Because often this is very dependent on each individual analysis, on each individual experiment, because what we assign as systematic uncertainty is related to effects in the experiment, which we cannot correct for, and rely typically on some kind of estimate for them. So so what work are you planning, and what aspects of systematic uncertainties are you touching here?
From the point of view, as I understood, the work group that was kind of working on this topic, they were talking more on generic level and trying to understand how it's possible, for example, to not do this experiment wise, but try to learn between experiments. For example, Atlas could learn something from CMS as well, and opposite way, and try to understand how better to integrate the systematics from this point of view as well in analysis frameworks or data formats. So as you see, through the all kind of like all these topics, there was the same discussion, how we could make it more generic and more basically to organize it in the way that it's probably could resolve some issues that experiments are facing now. But I think from this point of view, I'm not an expert in systematics, so I cannot reply you, but I would propose you, if you have any questions, you could ask Paul Ting-Yang to show their vision as well. I invite you, if you have any ideas, for example, there is to check in the report. So there is already, I think, pre-filled sections about systematics and their ideas how to resolve it problem.
Thank you. That is really helpful. Thank you.
Okay, let's see. Looks like there's no other questions.
Well, maybe I'll ask one. This is Tori. Very nice talk, Oksana. You mentioned in talking about analysis facilities that event by event analysis is basically fast enough now, and usability is more the concern. Do you think that'll remain true when the HLLHC hits, or when we get that big jump in data set sizes? Do you think we'll be back to worrying about making it faster more?
This is a very interesting question, and something that we are trying now to explore. So the idea is that instead of kind of trying to understand if we are fast enough or not, maybe we should try to try to imitate some kind of workflow, how it could look like for the user analysis for Helium LHC. And that's why, for example, me personally, together with Alexander Help, we are working on called Analysis Grand Challenge, where we're trying to basically design kind of workflow for end user analysis with enough data that allows us to see if from infrastructure point of view, if from, I don't know, ecosystem point of view, if from facility point of view, we are ready for typical user analysis that we think will be run by physicists during Helium LHC. And this is something ongoing work. We're planning to start to execute it next year. So we are already thinking about this. The goal of this exercise that it should be like easily re-implementable. For example, now we're also working with root team to have the same one analysis grand challenge implementation as well using root, and to start to compare and start to tune more on the large scale everything that we are developing, starting from facilities and finishing frameworks.
Okay, thanks.
All right. No more questions, then I think thanks to all the speakers. And we will adjourn in roughly a month, I think. Everyone, have a good day. Everyone.
Bye.